So, my name is Edwin Verplank. I'm a principal engineer with Intel's Network Product Group, Platforms Group, I should say. I was going to come up with a clever sort of name, why we come up with these terms of principal engineer. But I guess I spent enough time in research labs, and occasionally they let me out of these labs, and I can come talk to you guys. So,
Daylight.
sorry, say again.
Daylight.
Yeah, exactly. So I run a small team of researchers, about 6-7 guys, and we basically have been researching software-defined networks, network function virtualization for quite some time. And one of the topics that's really that I want to spend some time on is this platform. Well, I want to spend time on all of these pieces, but one of these topics called Platform QoS is really near and dear to my heart. I've been spending many years on it. It's a brand new set of hardware features that we're introducing, and specifically to consolidate workloads. So, we spoke about cloudification, network function virtualization, SDN, and they all have something fundamentally in common, right? You're going to consolidate certain workloads, whether you do that in the cloud or whether you do that in a telecommunications data center. Doesn't matter where you do it. If you're going to consolidate these complex workloads, you need some hardware assist to do so, and that's what I'm going to talk about. But you also need software enhancements, and that's what we're going to talk about in the packet processing piece, because packet delivery is, like Deepak referred to earlier on, packet delivery within Google, Amazon, Facebook has a slightly different meaning than packet delivery in a telecommunications environment, right? In a telecommunications environment, you have strict latency targets that you want to meet, and I'm going to talk a little bit on how we can meet those. And we've been researching those topics for a long time. Another topic I briefly want to talk about is some of the virtualization enhancements we continue to make to the platform, right? It's things like posted interrupts. We have a laundry list of hardware acceleration capabilities, and we continue to add to that to bring the latency down and the efficiency of running a virtualized platform. So, but before we do that, I want to give you a little bit of an intro on how a comms element is different from a typical data center element. So this shouldn't be a surprise, right? So we're in this software-defined infrastructure, and we're in this era where it's quite an exciting era. If you've been in telecommunications, you've been working in that environment a long time, and this is really the time where a pretty substantial re-architecture is taking place, right? We're moving from those fixed function boxes to, towards a standard server element. And what I would like to talk about is, how we can do that, right? And specifically the network piece, because that's in the end why we're all here. So, to depart the marketing content a little bit, there is essentially 3 elements I'm going to talk about. Now, there are many more elements that are important in order to facilitate the consolidation of these network elements. But from if you were to bucketize these, what are the 4 elements that come to mind, and specifically where our research team has spent a lot of time, and it's typically in the area of packet switching. So we have a software stack called DPDK, Data Plane Development Kit. Is you folks familiar with that? Yeah. No? A bit of it. So DPDK is basically a toolkit that enables real fast delivery of a packet. So we can enable the routing of a packet. We can increase that performance versus the Linux IP stack by about 25x. Right. So put that in perspective. If you take an off-the-shelf Linux distribution, right, and you install that on a server platform, and you take a packet in, and you route it back out, and you measure the time it takes from packet in and packet out, we can increase that by 25x by utilizing this Data Plane Development Kit. So there is a gotcha, of course, and the gotcha is that you have to port your application to this stack. You have to utilize these APIs, which is fine, which is what a lot of our customers have done over the past, including data center customers. So that's an element I want to spend a little bit of time on. Second element you need is an efficient way to virtualize the platform. We've all talked about, or Lynn referred to SDN, Deepak referred to NFV, talked about cloudification. Well, what do you need in order to facilitate that? Well, you need an efficient virtualization capability. So over time we continue to add more efficient ways to virtualize the platform. We have, again, a couple new acceleration capabilities that we're introducing with our latest platforms, and I want to briefly talk about that. And then where I want to spend a little bit of time as well is on the platform QoS capabilities. So if you look at our CPUs, specifically Xeon, right, we continue to increase the core count, right? We basically have, from year on year, we add, sometimes up to 4 cores, right? If you see where we are today, if you look at the Haswell platform, we have specific dies with 18 cores, right? 18 cores on a single socket. Hyper-threaded, 36 cores. They all have shared caches, right? We have a last level cache that is shared across all these cores. Well, what happens if you run, up to 20, 30 virtual machines on one of those sockets? They all contend for that resource. Now in cloud, that might be perfectly acceptable. But if you're going to consolidate, that doesn't work so well. And so what we're building is capabilities to partition off those last level cache resources and other shared resources in the platform. So that's what we want to talk about. And then lastly, I won't get a lot of time to talk about it, but not everything runs fantastic on Intel architecture. We'd be kidding ourselves if we could make that statement right now. That's not quite true. Think about DSP workloads, think about cryptography, think about compression, right? So if you go to Google these days, every single transaction, every single search that you do is actually encrypted. So think about the amount of data that flows through the net that's actually encrypted that requires to be decrypted, right? Now, if you have an appliance or if you have a server that does a limited amount of cryptography, then you could use the instruction set that we have to do so. But let's say you have an appliance which its only job is to do encryption, well, then you might choose for an accelerator. And over the years, we've built crypto and compression accelerators that do that sort of work. I won't have a lot of time to spend on that, so I'm going to spend much more time on these 3 elements. Does that make sense? Is that okay?
Cool.
Yeah? And if you have questions, just please stop me and I'll try and elaborate. So back to briefly to the open source community piece. So just giving you a high level idea of the areas of the platform, what we as a team been researching. So in order to get these high level, in order to get these communications performance, what we've been working on is basically deploying this data plane stack, so DPDK, in a virtual machine. But if you do that, you need to be able to talk to the virtual switching capabilities, you need to talk to the virtual instances of these network interface controllers. Right? So then you need to be building driver infrastructure and switching infrastructure in this kind of, in DPDK in order to get that performance of that virtualized, comms appliance. Right? So, because that's what you're going to do. If you're going to virtualize the network, you're going to run network applications virtualized. Right? So at the basis of that is a virtualized instance of DPDK. Could run Linux, but then you can't sustain the performance that we talked about. So that's one area where we spend a lot of time. We open source all these drivers, we open source the stack, dpdk.org, you can download all that and you can knock your socks off. Second piece we spend a lot of time on is virtual switching. So if you truly want to abstract the platform, then you need a virtual switch. So we've now been taking that really high performance IP stack, and we've been moving that into the host as well. And we've been making changes to Open vSwitch. You folks familiar with Open vSwitch? So we take that Open vSwitch, we deploy our DPDK in that, and then we can boost the performance of that Open vSwitch. Again, to facilitate the ability to virtualize communications workloads. Because they have a very different signature, right? If you virtualize a compute workload, if you need more cycles, what would you do? Well, I'll create more virtual instances, I'll launch a few more servers, and I'll be good to go. With a communications element, it doesn't work like that. If you have a virtual router or a virtual IDS, IBS, or you have some P gateway, some base station device, then there are certain latencies that you have to guarantee, right? If that virtual router says I support 40 gig, or 80 gig, or 100 gig, well then better if you're going to virtualize that, you sustain that 100 gig within that virtual machine, or 40 gig. and the latency is associated with that, right? Sorry, go.
With DPDK, I mean, are you effectively, with those calls, pushing the function back into the hardware, onto the controller, the NIC, to do the switching? So kind of like in a white box switch, right? You have a CPU that programs the chip that does all the hard work.
Yep.
And
No,
so-
we don't. No, we
No?
don't.
Okay.
Sorry to cut you short.
That's fine.
In the interest of time, we don't. We actually do all the switching on the CPU, but it's a very good point though, because that's the key takeaway. We're not going to a switch. We're not going to go in and request all support from the Ethernet controller, because then you're back abstracting. Then you're moving away again from that abstraction, and you can't move things around that easy.
Okay,
Right. So no, granted there are limitations, right? You won't be switching just yet 400 gig on a single core. We can't do that, but we're getting quite close to, 40. We do 40 gig on a core today. That's roughly what we do.
Okay, so in this case, the CPU is the important element that needs to support DPDK,
Yes.
and not. I'm seeing the mention of the controller XL710 family on there. Is that just a side issue? It's just what you happen to have chosen. It's not a dependency.
Not at all.
Okay.
We develop those drivers. We develop what we call POMO drivers, and those are the ones we open source. Okay. And they happen to support our entire controller range. Just happens that I picked the 40 gig NIC because we just launched that. That's
okay.
Sorry, it was another question.
So who the open source drivers and stack, who is that aimed at then? Who are you anticipating is going to take that up and play with it and do things with it?
Well, typically anyone that's going to develop an infrastructure element.
Such as?
We see Ericsson, Nokia, service providers.
Our original target, to be honest, were system builders, because it was very obvious that if you can get these I/O flows taking advantage of the parallelism in the processor and then able to walk Moore's law down with taking advantage of all those platform innovations without changing anything in software, that was the original vision for DPDK. And Edwin and I have been on this journey for many years together. What has been surprising about DPDK is it has ended up in hyperscale cloud deployments. Because it's dpdk.org. It's not an Intel-owned innovation anymore. We did initiate that community. We continue to contribute to that. But we're finding it in all sorts of cloud deployments worldwide, whether it's some of the cloud service providers, whether it's in private clouds, because it's so helpful in getting these network code flows moving efficiently, both at that high level as well as within an appliance or within a box, or even in use with NFV on a normal server.
Well, I mean, like if you think about like what got us to where we are with respect to virtualization now, containers and all of that, we've moved. The phrase, the top of rack is no longer the network edge; it's now the virtual switch, and that's very true in those kind of environments. And I think this is very important, especially for you guys to drill on with respect to all of the work that you guys have done, especially with Open vSwitch. Good grief, especially. And the reason for that is this is one of the biggest. I agree with you, however, points that often come up with respect to that move. So I think it's a good thing you guys should drill into.
Yeah, and we have actually a whole, right now I'm going to dive into a whole section. I just want to really ground you on the fact that DPDK is at the basis of most of this stuff. And
for sure.
Honestly, it just clicked when I heard that there wasn't too much knowledge about DPDK as a whole, so that's why I took that side tangent on giving you insight into why we did this and why we do this, to essentially give our customers the plumbing, and not customers, also the community, the plumbing, to go build out this new method of switching, NFV, SDN. That's why we're trending. So that's really what's in our mind.
And I'm sorry if I'm asking a question, sorry to ask, but for clarification, is there a dependency between DPDK and an Intel chip at the bottom, or can I?
It's a phenomenal question. I think, Lynn, you're way better equipped than I do to answer that than I can.
So there's not a hard dependency, but what we are contributing are optimizations that take best advantage of all of the parallelism and all of the features that are in the IA processors. So we've been doing virtualization optimizations for 10 to 15 years. So the virtualization VT, we have so many VT offload hooks associated with our processors. We've bucketed it as VTX. There's somewhere on the order of 10 of them, and they're in our Ethernet offload as well as just in the normal processor. And this has been something that has been taken advantage of by KVM and VMware and Hyper-V for many, many years. And so what we're really doing in our DPDK contributions is, because we have so much knowledge of what is in the platform, we're optimizing every flow so that you can just have your software abstraction layer and people call the library, and then it takes advantage of everything that's in that generation of processor.
Well, so like for this audience, I think it's also important to point out, just because this is how I think it started to click for me, like none of us, I think, will do that. I think it's important to really call out your integrations with things like OVS.
Perfect.
Because that I will use. I will use that.
Right.
Perfect. Good. I think we're all grounded. DPDK as a basis. It's BSD licensed. Any developer can go take it, design for it. We provide infrastructure for optimizations for our platforms. ARM can do it. PowerPC can do it. MIPS can do it. As a matter of fact, we enable those guys as well. They can. We won't go and do an ARM port, but all the tools and capabilities are there to do that kind of thing. So.
Yeah, I would think of DPDK, think of it as a library. It's
Exactly.
a library that software can take advantage of.
Cool. So very briefly on open source, I will get to things like C groups and perf and what we do there and what we open source in order to give you better controls to guarantee performance. So this is the platform QoS piece I keep referring to. So good. So now why do we do it? Why do we do this? Right? Why is it that we have been making these optimizations to OVS? And this is the fundamental reason. If you take, and again, if you're not familiar with Intel platforms, we recently launched Intel Xeon D platform. It's called Design Efficient. It's a Xeon-based SoC. This is basically our mid to low range Xeon part. If we take this out of the box, we take DPDK and we do a bunch of forwarding, we basically do about 60 gig at 64 byte packets. This is a pretty good number, right? This is by and again, no hardware assists. This is all done on the core, right? So we take one core, and in this case, we have 8 ports, 4 cores, and using those 8 ports, 4 cores, we can do about 60 gig. Big number. Now you take your OVS out of the box, and you do a similar exercise. You're gonna take that packet into the soft switch, and then you're gonna packet switch it into the guest, then you're gonna turn it back around, and then you're gonna measure the amount of traffic that came back. Right? So here we do 60 gig, here we do 350 megabits. So now go back to the fundamental problem we're trying to solve. We're trying to consolidate communications elements. If we go to our dear customers and we say, hey, you really need to use this soft switch and you really need to scale your performance and go and address this new initiative that we're talking about, they're going to turn around and say, go away, we can't do this. So then the fundamental question is, what happened, right? Why is the performance so bad? And then granted, you take a copy and you switch the packet in, you maybe expect half the performance. But we don't even do that. We do a fraction of the performance. So then we went away and we said, okay, what do we do to fix this problem? Well, first we needed to do some analysis to what the problem really is, right? So then we use vTune to do all this stuff, and then you come to the conclusion. You spend the majority of the time in the Linux kernel, then you spend a bunch of time in the hypervisor, and then finally you spend some time in the switching stack, in OVS. And it's a huge number of cycles. So this is like a 10-second run, 34 billion cycles spent in Linux. Well, that's not how you make money, not by spending time in Linux, right? So when you drill this further down, you actually see that you're spending time in memory allocation. So you don't need to understand all this, but the issue is that when you see SKB, it means that you're spending time memory allocating. So what happens is, for every single packet that arrives, Linux gets an interrupt, and it says, oh, I better go and allocate some memory because it looks like I have a packet pending. So it allocates some memory, DMAs the packet in there, and then the NIC says, hey, I've put the packet in memory. Linux processes the interrupt, says, oh, there is data there. Processes the data, packet copies it in a different space, Go processes it, switches it in the guest. That's how you get to that number of 350 megabits, because that path is way too long. This is actually the fundamental reason why we came up with DPDK. We avoid all of this, And we pretty much avoid all of that. And then we started looking at the OVS switching stack, and we realized that even there, it isn't quite well optimized. It is reasonably good for big packets, but as soon as you start scaling down, it really doesn't look good anymore. So, what can we do to fix that problem? And now I want to briefly talk about some of the things that we've been doing in the stack overall to try and optimize the performance. And then you have other options as well. It's not all about soft switching. You could potentially utilize pass-through. So if I use the term pass-through, you familiar with that? Yeah. So it could enable SRIOV, you could take a NIC, you could switch it right into the guest. And then you could turn the packet round into the guest, could switch it back to the NIC and then to another virtual machine or back out the platform. That's not very efficient. You could do it, and it's actually being done today. The other thing you could do is go back to your traditional architecture and say, hey, I'm going to use a Tor. It's not very efficient either, right? Because you're back to dependencies on Tors. So one of the things we've been working on for quite some time now is actually optimizing that OVS piece. And then targets we set for ourselves is 40 gig line rate. And in the interest of full disclosure, typically our Xeon D platform is capable of about 80 gigs, and our EP platform is on a single socket is capable of 160 gig. So we have the capabilities to do so, except for the fact that this is assuming native performance, right? So this is a bit of an apples to apples and oranges comparison, but the target we set is 40 gig for soft switching, taking in mind that you're going to take a packet copy, right? So what does that look like from a sort of block diagram perspective, and just a tangent? When we say, these two diagrams are effectively the same, but there's a slight nuance. We've introduced this product called Red Rock Canyon. So this is from our former Fulcrum acquisition. You guys might remember we acquired those a number of years ago. We continue to design switch capabilities in that division, and they've developed a low radix switch, which is effectively a 100 gig NIC, and it has a lot of switching capabilities. It has a pretty flexible, they call it flex pipe. So what you actually can do is we can develop APIs here, and OVS can go set up the SRIOV functionality within that chip, and as a packet comes in, we could dynamically change the flow, right, and steer it to one of the virtual machines, something we could do. The only limitation here is that you can only support up to 32K flows. So it's not going to give you a lot of scalability. Then the other capability you could use is the SRIOV functionality within a 40 gig NICs. But you don't have the same flow functionality as here, so this is either a little more difficult to scale. But from a performance perspective, these two solutions will do considerably better versus soft switching. This is how you get to those big numbers of 80 gig and 160 gig. However, where we are at this moment in time with our CPU architecture, we can do 40 gig with this sort of solution, and that might be acceptable for the market we're trying to address. Does that make sense? So it's a trade-off between performance and flexibility. This gives you ultimate flexibility because you can runtime control where you're going to steer a packet. Here you depend on the hardware functionality to actually get that packet into the right location. Right? Right, so how do we get there? How did we get, and actually so as a matter of fact, last week we actually hit the 40 gig number in our labs. At the time when I was putting this deck together, we actually hadn't hit that number yet. But as of last week, we were able to do 40 gigabits soft switching in our labs. And the way how did we get there? We utilized this data plane developer kit as a basis for our switching. We minimized the number of VM exits, right? And when we made some OVS optimizations, and then this is important from an OVS perspective. I showed you that. I'll show you that in a minute again, right? I showed you that VTune shot all the way on the side here, where we spend all that time in the OVS stack. And the way we squeeze that portion is by actually doing these sorts of things. So rather than pulling So we go into a poll mode scenario. So rather than becoming interrupt driven, which is not a good thing. So think about so the Linux stack. It pretty much is an interrupt driven IP stack. So what happens is the NIC receives a packet. It'll typically know where to DMA it to, because it has what we call a receive descriptor, and it will tell it has been set up in advance to where to DMA to. So it DMAs to that address, right? And then it generates an interrupt. So interrupt gets to the CPU. All the time that data is just sitting in memory, right? That packet is sitting in memory. Generated interrupt gets to a handler in the kernel. Now if that core is in user space, it comes to kernel space. It'll go and read, okay, I need to go and process. It will go and read what we call the interrupt descriptor table to figure out what interrupt it needs to process. Goes and runs the handler. Oh, this is an Ethernet packet. Oh, I need to call this Ethernet routine in the kernel. Calls the Ethernet routine in the kernel, and then finally it gets the packet, and then it says, what do we need to do next? So you're spending millions of cycles.
So why would you not be using DPDK right now?
You have to port. It's all about backward compatibility. You have to port your application to DPDK. Right. So now we've been designing ways to re-inject it. So we've been designing ways to take the packet, right, in a fast path, and then selectively say, hey, this is one that goes back in the Linux kernel, and this one goes to our fast application.
Yeah,
So-
I would think of the situation as very similar to trying to do cloud-ready applications. If all you do to get an application in the cloud is you compile it to a specific PaaS environment and just plop it into a VM, you're not necessarily getting all the benefits of the RESTful design methodology, for example. And so it's very similar with DPDK, where if you already have existing code and all you do is you port it over to a new environment, you're not actually taking advantage of all the parallelism and all those optimizations. So it takes a little bit of some rework and rethinking of the design of the flow, very similar to cloud-ready applications. It's just network-ready applications.
I think maybe before today, I was thinking it was, essentially something part of OVS to install that library, integrate with OVS natively. But now there's other integrations within the guest VMs to actually leverage those integrations. Is that
We now have a pretty. We've been on this track for 5-6 years.
Yeah.
So we have a big set of libraries. As this might seem a fantastic idea, and it is a really good idea, but it's not something we pick out of thin air. These things usually are in progress for many years, right?
Yeah, in fact, one of the aspects of the Fast Track initiative is to do a Network Builders University, because we find that people don't necessarily look through all of the lists of the optimizations and the libraries that they can integrate to get the highest performance and speed. So it's really a university style training that we're giving all of the developers out of our experiences, and finding that as people try and move to this new paradigm, they've missed something and they're wondering, why are my line rates not what you're getting? This is a way for us to package it up and make sure that everybody can get that same benefit.
So basically, essentially, like DPDK becomes this abstraction layer for you to say, well, okay, so you can keep calling network resources in much the same way from a developer's perspective. So OVS comes in and writes their module. They have to leverage the DPDK library, but by and large, they're not really asking for anything differently. They're certainly not trying to become aware of the parallel processing.
No.
That's what DPDK does.
It's done
like,
for you.
Yes.
Hey,
It's done
give
for you.
me a resource.
Yeah.
DPDK says, cool, I know how to do that. I'll handle it in the back end. Is that accurate?
Yeah, that's very accurate. There's just one little gotcha, right?
Yeah.
It's a pretty substantial gotcha. For instance, if you want to remain OpenFlow compliant, right? We the DPDK community has to make sure that when the request for a new flow setup comes in, the DPDK responds to that and goes and sets that up. But that's okay. Those are things we are doing. Those are things that the community is building and integrating. And the way that it works is when you bring up OVS, you have a set of ports that you might not care too much about because you have slow traffic, but you have a set of ports that you might want your fast path to live on, because those are the ones you're going to associate with network elements, right? So
do you change the rules with respect to reactive versus proactive flow instantiation, or is that?
Not yet. Not
Okay.
yet. Right now, that's just generic.
Okay, gotcha.
Just generic.
Thank you.
But really good question. So I think you guys got it. It's really good. This is a lot of information, right? Because it's we have to go several years back to give you the view of DPDK, and now we have all this forward-looking stuff coming down the line as well. So
Yeah, but again, I think this is the missing piece, because we've moved to this model out of necessity, we were just missing this piece to make
Yeah.
it really, really viable. Certainly for the large,
Exactly,
you know, the
exactly.
large, the large customer base.
And this is I go back to the point we've all been trying to make, right? If you want to consolidate, and this is the pieces that, you know, why Lynn and Deepak asked me to come and fill in this area is, hey, we're going to talk about this ability to consolidate and these new ways to, you know, increase your agility to do service delivery. And well, you need to consolidate this first, right? You need to meet the performance requirements first, and that's what I've been concentrating on for many years together with the research team. We've been building these kind of capabilities for a long time now.
You know, right now, a lot of incumbent network vendors, their performance, you know, is terrible for virtual appliances, right? Firewalls, IDS, IPS, things like that. So, have you seen network vendors try to use DPDK to develop like their next generation?
Oh yeah.
Oh yeah.
Virtual
Oh, yeah,
firewalls,
yeah,
things like
yeah,
that?
Yeah, absolutely. And what's really also interesting about many of those vendors is they're starting to offer hardware and software appliances. And so in Network Builders, for example, we have a number of McAfee appliances, and you can get them as hardware or software. And so it's really just what is up to you and what works. And a lot of those are starting to pull in DPDK. In fact, part of being in Network Builders is you're beginning to pull in the DPDK optimizations.
So this really starts to pull up the NFV side, the virtual appliances, up to getting at least very close to the hardware level for a lot of platforms.
Right,
Certainly if you're distributing, I can see that.
right.
So let me try and get through this, and because I'm gonna run out of time in no time here. So let me try and get through this, because there's two other topics I want to give you a really good insight in what we're doing from a hardware perspective to get it to the next level. So we do this. So rather than processing one packet at a time, we process bulk, and we don't do this interrupt-driven thing what Linux does, because that's terrible. And that's what we do first. So we basically monitor, okay, how many packets do we have in the packet buffer? If we have 32, then we're gonna go and process them. Way more efficient. You amortize, rather than going to, fries, for every single food element that you need. You're gonna go store it all up, and you're gonna go and get them at once. Same with flow extraction. So one of the things you need to do is go and figure out what you need to do with this packet, right? So you get a packet, and then you need to go figure out the OVS switch needs to what we call extract the metadata. So it needs to go and figure out, okay, what kind of packet is this? Is this VLAN tagged? Is this VXLAN? Is this GRE? Is this NVGRE? What kind of tunnels am I supporting? And you need to extract all that, and you need to stuff that in a specific structure. You spend quite a bit of cycles on that. So we optimize that part of the routine. Then we're going to go and carry out certain actions, right? So you get that packet, and then you need to go and figure out, is this something that needs to go through a firewall, or can I just route this back out, or is this something that needs to go through a certain tunnel, right? Then that is what you do in that process rules bit. And then finally you have an enqueue function, right? So you figure all that stuff out, and then you enqueue the function into the next stage. This is again pretty important, because if you enqueue a packet at a time, you incur that context switch latency I was talking about. So what's much better is to do these bulk allocations here as well. So you wait until you have a certain elements filled up in that queue, and then you flush them all together. That's not going to work 5 minutes.
Like Nagel's algorithm, right?
Sorry, excuse me.
It's like Nagel's algorithm.
Exactly.
As you speak.
Exactly. Right. So where did we end up? So this was that picture I put up first. We have all that time in Linux, all that time in KVM, all that time in OVS. And then when you do it after our optimizations, you actually see that all this stuff disappears, and you spend time where you want to spend time. We spend time in the switching stack, and all the other stuff has disappeared because we're not VM exiting in the host. We're not doing memory allocation anymore because that's all done in advance using DPDK, and we're actually spending time where we want to spend. And with that's how we got to 40 gig performance. And then we're doing a lot of other stuff to get beyond that 40 gig limit. So back to what we're doing in the open source community. There's actually a link on here. We release all this stuff on a public branch of OVS. Right, so let me just briefly let you guys take notes. So one other element, or two other elements I briefly want to talk about, and seriously, how long can I run over? Because I'm not going to be able to squeeze this in 5 minutes.
You can go over a few more minutes.
Yeah, thank you. So on the virtualization side, and like Lynn indicated earlier on, I'm not sure how many acceleration capabilities we have, but we've developed a whole bunch over time, and all to minimize the overhead associated with that with virtualizing a workload. We also made some very specific ones for communications, and it's, for instance, large page table support in our IOMMU. So we have this. Showed you that pass-through model earlier on, and the element that does the pass-through is called the IOMMU, and it essentially remaps a physical address to a guest virtual address. So the address so if you generate a DMA transaction, or if you generate a PCI Express transaction, it always leads with a physical address. And what the IOMMU does, it remaps that address into the guest virtual space. So the hypervisor doesn't need to touch it, right? And that's essentially what we do with that. And then we made an optimization to limit the amount of page walks that you do for address translation. Ultimately, what it means is we can now sustain native performance when you do that pass through. It's really important. But the three pieces I want to spend a little bit of time on is posted interrupts, something called VM-Func, a hardware optimization that we're using for virtual switching. And then lastly, we have some FPU optimizations, and that's where I want to briefly start with. So, the FPU is the floating point unit, and it's a special unit that many applications use. So think about if you do video transcoding, or if you do even when we do DPDK, we actually use these AVX instructions to do a vectorized POMO driver. What it means is we basically take, so like I said, we bulk, we put in 32 packets in a queue, and then we allow the buildup of 32 packets, and then we flush those packets all in once, and then we use vectorized instructions. So we have instructions that allow you to basically pack double words in these registers, and then we can do parallel instructions on all these double words that get squirted out into the result of one big massive 256 byte register. And that takes way less cycles than when you do that than when you're going to do that 8 bytes at a time, right? So basically you pack up these registers with several packets, then we run one operation to basically push all these packets through into one output register. And that saves you a bunch of time. But there's a gotcha. When you do that in a guest, and 9 out of 10 times it all goes fine. So we have this when the guest execute, the CPU is in this mode called non-root. We come out periodically for housekeeping, things like timer injection and other stuff, garbage collection. The Linux kernel and Windows does that. We VM enter, we process packets. We VM exit, we do housekeeping. We VM enter, we process packets, and we come out. And then somebody decides to use the FPU, right? Because previously, if there's no FPU usage, you don't need to save and restore. Everything is cool, the state remains, and you can just continue. But if somebody under the hood uses the FPU on that core where you're processing packets, you have an issue. Because out of the box with Zen and KVM, they use this algorithm called lazy restore. So you want to go and process packets, but the FPU is not available. So now you come back out, and now you have to restore the FPU. And that's really, really expensive. And if you want to do that, if you're not from a monetary perspective, but from a time perspective, it's really expensive to go do that. So what we then propose is an optimization to this to eliminate this 10 microsecond latency, because that's what you incur. Right? So just put it in perspective, right? You're processing packets, and occasionally you go away for a microseconds, but then all of a sudden you're in you're transcoding voice or you're transcoding video, and you get this huge, pixelation in your stream. Well, that could be a result of this floating point unit not being available for that portion of time. So we developed this patch to eliminate that. I don't want to waste too much time on this. We have tools to identify that. And so what we do is actually before every single VM enter, we're going to go and check whether the FPU has been used or not. And recently we pushed this patch upstream, and now we can minimize the time from 10 microseconds to 2 microseconds. So now you don't have that pixelation anymore. right? So that's really what it results in. Really, really important optimization we just pushed in as of a few weeks back. Now, finding this issue, that was a whole different ballgame. Because somebody just reports, hey, I see pixelation, or I see this, I'm dropping frames, what the heck's going on? Well, to go from that level down to this level, that takes a few months. So to talk about it for 5 minutes, there is about 6 months worth of research behind it. So.
It's true for everything, right?
So, okay, posted interrupts. Without boring you with all the details, if you talked about these VM exits, right? So when you incur an external interrupt, and when you're in that non-root mode, you will, in the past, you'd always incur a VM exit on the occurrence of an interrupt, right? So and think about the integration of accelerators, right? Because I just told you, well, you shouldn't really be doing interrupts. But what if you have an accelerator that only is used a portion of the time, right? You don't want to pull that thing every microseconds, because you're just burning power that you don't need to. So in some environments we use interrupts. Accelerators is a good example. So when we generate an external interrupt and it gets to the CPU, in normal cases you always VM exit. What we've developed is a mechanism called posted interrupts that essentially stop that external interrupt from occurring. So now you can continue execution when that interrupt occurs, because we've built something that tracks where the guest is running, because that's the reason why you VM exit. Because at the time of that interrupt, you might either not be scheduled, right? Your virtual machine might not be scheduled, or it might have moved to another virtual CPU. So what we do is we've built now some hardware that tracks the virtual machine and figures out and it also knows whether it's running or not. And then you don't need a VM exit anymore, because if you have that data, you can route that virtual interrupt to whatever core where it's running, right? So what does that mean for a developer? And this is essentially what it means. If you don't use posted interrupts, you end up with that. So we have a test harness. Test harness has a timer built, FPGA with timer built in, generates tons and tons of interrupts, and every time when it generates an interrupt, it starts a timer. And then the first thing we do is basically we stop the timer, and then at a later moment in the handler, right? So that interrupt gets to the handler into the guest, and then we come back, we stop the timer, and then we dump all these samples. And then this is the sort of picture what emerges, and it's really, really cool, because with posted interrupts we generate this really nice narrow band of samples, and this is even without real-time optimizations. And that's the key here. Normally, to get to this sort of narrow band, you need to do all sorts of stuff to your software stack. And now we're demonstrating that, hey, actually, we've got some pretty cool hardware hook here that allows you to give you near real-time interrupt processing without the need to go to your special software stack. So now tying it back to the reason why this is important, back to the communications workloads, back to the storage workloads, back to those compute elements that have tight timing requirements. You use this to get your data in, right? And now you don't have that huge jitter, right? And this is the kind of stuff that all the data center customers and the telecommunications customers will use to essentially build their appliance. Make sense? So, other thing we've designed, or actually this was we have an instruction called VM-Func. And VM-Func enables you to request assistance from the hypervisor without VM exiting. So normally when you do a paravirtual call, or when you paravirtual, not such a good example, but we have instructions like VM call that calls so you can call an instruction called VM call, and that causes a transition to the hypervisor. But there is issues with that, because that takes a lot of time. So if you need assistance from the hypervisor, you either use a PV call, right, paravirtual call, or you utilize this new instruction called VM-Func. And VM-Func has a new flag with it called EPTP. This is a page pointer, and here is how it could work. And this is actually something we're about to open source. So back to the Open vSwitch example, what you can do is a packet comes in, gets into the vSwitch, we allocate the packet buffer, which is what we normally do, And then normally we go into OVS and go into all the software enhancements to get the packet in there, and there's overheads associated with that. It's with what we've shown, right? But what we've developed is an instruction that allows you to change the packet pointer within the virtual machine to an area where the packet is living. Right? So now you put that packet in memory, you change this pointer within the guest to where it's living, and now you can just go get to that address.
You're not actually copying it in that case.
You're not copying it.
You're just moving a pointer. Awesome. That's actually really cool.
That's cool.
So this was an instruction that we had for quite some time.
Yeah.
And then I looked at it and I'm like, man, this is silly. We can use this for soft switching.
Yeah.
So now we're developing a prototype that's going to go out and we're going to build this.
Wow. That's awesome.
So we think this will give you. So this gives you a secure way and a fast way to switch packets. So. Right. So something I want to spend the last sort of 5-10 minutes on, if that's okay with the. Good. So again, this when we talk about this might seem really, really obvious, but this is something which has been in the making for a good number of years. This is not just an idea again, which all of a sudden comes and we just have it. No, this has been in the making for a long time. Been working on this for many years. I'm actually one of the lead architects on these technologies, so this is near and dear to my heart. Spent many hours in our labs prototyping and building and writing code for this, and it's really cool. Of course, it would be. So yeah, that was pretty bad. So we have these new sets of technologies called cache monitoring, memory bandwidth monitoring, and cache allocation technology. And now it's pretty obvious what's going to come here in this box in about a year from now. So we're focusing on cache now, so I guess you'll know what's going to come next. So so essentially, like I said at the start, we have a big number of cores and shared resources. If you want to provide QoS, and if you want to provide privileged certain privileges to a virtual machine that you really care about, today you can't do that. Right? We have these shared caches. Whoever fills the fastest wins. So if you have a virtual machine that does something latency sensitive, like a communications appliance, and you have a virtual machine that's doing video transcoding, video transcoding is known for its really nasty effects on the last level cache, because it just streams in, and it doesn't. The transcoding algorithm doesn't necessarily get to the data before it's done with the previous set of data. So what happens is that data gets evicted and it goes and fetches it again, right? Because we use prefetching. So the problem with that is that you're overfetching, but you're never using the data. But the effects of overfetching means that you're going to evict other data from the cache as well that you really need for your real-time application. So that's the fundamental thought why we've been designing these hooks. And then we have we have a set of monitoring technologies that allows us to basically monitor the last level cache occupancy on a per thread, per core, or per application basis. And then we have a set of hardware features that essentially goes and monitors the memory bandwidth on a per core, per thread, or per application basis. And that's different from we have these big block called perfmon, so lots of performance counters, but they are typically hard to make certain applications decisions on. So these monitoring capabilities, they've been designed for orchestration software to actually take decisions on, because they report much more easier numbers to interpret. They'll give you numbers like, here is the number of kilobytes that you have in your last level cache that's associated with this application. So if that's an application that you don't care about, well, you might want to shrink that, right? And that is what we're doing with cache allocation. So on the allocation front, what we can do is we can control the amount of last level cache that we associate with an application core or thread.
And what is the interface to this? Is this still DPDK, or is this something
No,
else?
model specific registers.
Okay, cool.
So we have APIs, again open sourced, and I'll show you a set of links in a minute.
Cool.
Right, that allow us to set all this up, but there is hardware right underneath the hood that takes care of. So we basically on the monitoring side we introduce a hardware concept called a resource monitoring ID,
Gotcha.
And the RMID enables you to track an application. So what we do is, and this is where the C groups becomes really important, we have a new C group. So for those folks familiar with containers, they might also know what the C group is, right? So what you can do is you can associate the container with the C group, and then you can wrap certain performance boundaries around that.
Yeah.
So a C group is a control group. You can say this C group, this set of applications only gets this much of CPU cycles. Now we've built a C group that essentially allocates a certain amount of cache with that container, application, core, thread, whatever. You take your process ID, or you take your virtual machine, or you take your container, you echo it into that C group, and then automatically the scheduler will make sure that as you move that container to a different core, your class of service associated with that core is that amount of cache. Does that
awesome.
make sense?
That
Yeah?
is cool.
Yeah. So, but in order to do that, you also need to go figure out the amount of cache that you need in the first place. And that is where you use this cache monitoring functionality, and we have an open source application called Perf that's been enabled to take advantage of this. So with Perf you go and monitor, and then with the C group you go and allocate.
Okay, so is it more, I guess on the C group side, is it more dynamically allocated, or is it like sort of, I guess you have to sort of specifically allocate that space? Is it
Exactly.
automatically discovered, I guess is my question.
So what you do is, it's not automatically discovered. What you do is you as a developer, right? You have to go and figure out the amount of cache that you need at the start.
Sure.
And that is what's input into your cache allocation C group to go and set it aside, right?
Okay.
But the monitoring will allow it to scale, right?
Yeah, exactly.
Okay.
So that's honestly where I'm asking feedback from you, right? So
So via the API, you're going to be able to say, if I reach this threshold,
Exactly.
Oh.
Now what is that API?
see, I'm waking up now.
What is that API? Where does it live?
Because I mean, you could be starting your video transcoding at the beginning,
Yeah.
and then towards the middle of, you run a container halfway through that, and then the video transcoding finishes.
Yeah.
So your resources are
Exactly.
different.
Exactly. So now
Halfway through the job,
Yeah.
the C group has existed already.
Yeah.
So you have to then, I guess, constantly monitor it and make improvements.
Exactly. You have to then, once the resources are relinquished, well, you want to get it out of that C group, right?
Sounds like-
You want to,
It's a lot like ballooning.
It is ballooning.
Yeah.
It is ballooning
I was
at the
trying to think
cache.
of that. That's
You're,
exactly what it
you're
is.
absolutely
Yeah, yeah.
right. It is ballooning at a lower level.
Yep.
Right now, what I'm asking from you is, what are the software orchestrator, Nova, Ceilometer?
What are the use cases?
What are the use cases? Who does it? Who's responsible for it? I really don't know yet. So now, what can you do with this stuff? And here is an example. We took a couple of weeks back. So we took our favorite Open vSwitch. We let it run out of the box with no competition whatsoever, right? And then we monitor, right? So we see that we need about 5 megabytes to sustain 12 million packets per second. This is pretty good. This is near 10 gigabit line rate. That's what it means. So then we take our two favorite aggressor workloads. We take application called Stream, an application called Alembench, and we let it go nuts. So what happens is our occupancy drops to 4 megabytes per second. Oh, sorry. Our forwarding performance drops to 4 million packets per second, and our occupancy in the last level cache is down to 840 kilobytes. Which means we can no longer sustain that 12 million packets per second because we need 5 megabytes. So I guess it's obvious what we do next, right? We go and instrument it. We say, hey, you know what? I really care about this Open vSwitch product, right? I want to sustain the performance. I'm going to allocate 5 megabytes of last level cache with it, and I'm going to rerun this experiment. And we can sustain the performance of a few points.
Does that then result in a reduction of performance for the other applications?
Absolutely.
Yeah.
You have to make choices.
Sure.
to make
But at the very least, this gets you an idea of what you want to promote in the CPU. And I guess the reason I asked if this was a map into DPDK, I guess it doesn't have to, but this would be a no-brainer to map things like DSCP values and cause values directly to queues like this.
Absolutely. So we're developing APIs right now.
Sweet.
And we have them open source that together with DPDK team. So now we have a big, pretty substantial engineering team that's working on DPDK.
Sure.
We're working with them to make sure that they get these APIs. So we did the same prototype on containers. So I need to finish up. Barbara's giving me a
Talk more over lunch.
very awful looks. I don't want to see those. Containers, we did the same thing, trying to restrict. This is actually discussion I'd like to have pick your brains on a little bit. Containers in comms, or at least containers in network infrastructure, is a little bit tricky because they're typically short-lived, and network infrastructure is not short-lived. So give us some feedback on this particular usage model where we spawn away a container, right? That's going to do some intrusion detection, and when it's done, when we're going to relinquish the resources, and what we do is we limit the amount of cache these containers get, so it can't turn into a denial of service attack. So a whole bunch of links. Again, back to the open source contributions, right? This is all open source, so it's BSD based. It's AlkyML, so we have kernel patches. As of kernel 4.1, our scheduler hooks for platform QoS are mainstream, so you get a cache allocation, C group, you get perf with CMT support. The OVS work, not on here, is on the previous slides. OVS 2.4 branch is enabled with OVS or at OVS DPDK. Then we have also some homegrown tools, PCM, that we're enabling, homegrown tool called vTune that we're enabling. And that's where we're at. So, well, you guys can probably do the key takeaways better than I can, but DPDK was actually quite eye-opener that we clearly hadn't done a good job yet at getting the message out. So this is important for us to take home, that we need to make sure that message gets out. So I want to encourage you to give me feedback on, or give Intel as a whole feedback on where we need to spend time to make this happen, right? So I talked about C group, I talked about perf, we talked about DPDK. What are the other open source programs where we need to spend time? Do we need to build more intelligent orchestrator? We're not necessarily the right team, or the research team that I run isn't necessarily the right team. We build plumbing, but to get feedback on where we need to influence, that would be really, really, really good. So virtual switching, I think it's getting there. We're up to 40 gigs right now. I think it's pretty exciting time. With those modifications we talked about, we think we're going to scale quite further. And then lastly, I think we demonstrated over the number of years that Intel architecture, with all the optimizations that we've made, integration of memory controller, integration of PCI Express, integration of QoS, integration of capabilities in our NICs, it's actually becoming a pretty good platform to move packets around the network.